Kevin? Huh? Yeah, about time you put your hand up. What we're going to do, I don't know how many of you remember that it was 45 years ago when the activities that Kevin mentioned were ended. Now, we did not take moon cheese or find any up there, but I have a few packages here that I think these young people would probably like to have. Anybody else like to? There you go, one more. We'll try that. I didn't play baseball or football. It's hard to believe it's been 45 years, Kevin, but since the last person, namely yours truly, stepped on the moon. Neil Armstrong was number 1 and I was number 12. Apollo 17 was designed primarily as a mission of exploration, and everything went very well. The equipment worked well. We had no significant component failures. It really was a tribute to the 450,000 people, most young men, but supported by many, many others that made Apollo possible. It was, and it was young people. You'll find that anytime great things are done by Norwegians or by Americans, or really, I think, anyone in the Western world at least, that we were young. The average age of the people in mission control during the Apollo 13 crisis was about 26 years old. It's hard to believe, but that's the way it was. Now, this valley on the moon is the valley that we explored. The landing site, our landing site was there. This mountain is about 2,100 meters high. So the valley itself is a little deeper than the Grand Canyon of the Colorado in the United States. And we were able to land with what they call an error ellipse of about 1 kilometer radius. For a while, it didn't look like we could land there at all because the error ellipse, the initial error ellipse included the mountains. But that was very conservative. All the Apollo missions landed within a few hundred meters of where they had planned to land before they left the moon. And by the way, in our training, we had pretty good simulators that illustrated the craters and other features of this valley. So it wasn't as if we were going into a place that was totally unfamiliar. Just to give you a contrast, this is Storfjord, the village of Eksun here, Ekøy here, and my field area in Norway. And 12 years after I was exploring this part of the Earth, I was on the moon. Things happen very fast, you might say. That's where I lived, in Selborg. But eventually, I ended up on the moon. This picture illustrates symbolically many of the aspects of the moon missions. Scientifically, we learned a great deal about the moon, symbolized by the South Massif behind me. The technology that put a human being on the moon was really quite remarkable for its time, but very, very primitive compared to what this computer here, this laptop has. But still, it worked, and we depended very, very much on the computational power that they had in mission control and elsewhere on Earth. I think it's very important that free human beings made this possible. And then, of course, what we learned on the moon relates directly back to our own Earth, and we may chat about that a little bit more later. The Apollo space program, just as a quick review of landing a man on the moon, was proposed by President Kennedy in 1961. It was a part of the Cold War between the Western world and the then Soviet Union. It was a major competition during that time, and the first mission that visited the vicinity of the moon, of course, was the Apollo 8 mission. And that occurred in 1968, around Christmas time. I think some of you probably are old enough to remember that. I see a few heads. That was a mission we never expected to fly. And it came about as a result of delays in the testing of the lunar module, concerns about what the Soviet Union might be up to. But because of those delays, George Low, who was running the Apollo Spacecraft Program Office at the time, decided that we needed to keep the momentum going, and so an Earth orbit mission was converted to a lunar orbit mission with Frank Borman and his crew. Neil Armstrong then, of course, successfully landed on the moon on July 20th, 1969, and that basically ended the moon race as far as the public was concerned. But talking with Soviet emigres, they felt the first time we successfully flew a Saturn V rocket, which we'll talk about more in a moment, that really was the culmination of the so-called race to the moon. There were 5 additional Apollo missions after Apollo 11, and those missions not only further demonstrated the technological achievement, but began the true exploration of another planet, a small planet that we call the moon, but nevertheless true scientific exploration. Apollo 13 caught the public attention because of the damage to the spacecraft due to an explosion in an oxygen tank, but was rescued primarily through the efforts of the people in mission control. Really a remarkable achievement. The last 3 Apollo missions each explored in detail for 3 days a different part of the moon, but even with the 6 landings on the moon, we have only begun to, pardon the expression, scratch the surface of our understanding of that planet. But we have gained a great deal from that exploration. 850 pounds of moon rocks and soil were brought back to Earth by these missions, and the studies of these samples continues today. You've heard about gifts that keep on giving. Well, these certainly do. But part of the reason is because of the advance of analytical technology in the last 50 years. And so you can keep going back even to the same samples and get new information about them. And there were scientific experiments left at 6 sites on the moon. They operated for quite a number of years, giving us information about the internal structure of the moon, the exosphere, the very, very thin atmosphere around the moon, and other information. Those experiments were turned off because of a reduction in power and an increase in cost by about 1977. They were powered electrically by a radioisotopic thermoelectric generator, RTG. And I had the privilege of handling a little cylinder of plutonium on the moon. It's fine. I mean, it's just a little warm, you know. From a science point of view, because there are many other benefits of this all having happened technologically, but from a science point of view, the primary value of what we have learned so far about the moon is understanding the very early history of the Earth. The moon has recorded that early solar system history that the Earth was exposed to, and so as a result we now know what was happening in the first billion years of Earth history that has been obscured to us here on Earth because of the dynamic nature of geological processes here on this planet. And so from my professional point of view, that understanding is extraordinarily important. And I think it's important philosophically to everyone because it's in that first billion years that life was beginning here on Earth. And we now know it was those beginnings were taking place in an extraordinarily violent environment. And we still don't fully understand how that combination of violence and the development of the precursors to replicating life forms occurred, but there was a relationship, and we're still trying to make sure we understand. I think I understand it, but I don't think anybody else would agree with that. Okay, now I throw this in. People often hear there were no pictures of Neil Armstrong taken on the moon. Buzz Aldrin was handling the camera and didn't see fit somehow to get very many pictures of Neil Armstrong. But this is a picture of Neil Armstrong working with the rock box, where he had put really a fantastic collection of rocks that he had picked up in about 20 minutes around the Apollo 11 Eagle spacecraft. And he was putting those rocks in the box. And Neil told me later, Neil and I worked together a great deal, he told me later that when he looked at that box, even though he had a lot of rocks in there, it seemed somewhat empty. And so he started shoveling dirt into that box. And that dirt sample, what we call a regolith, the dirt sample is probably one of the most valuable samples that has ever been taken on the moon, because it has allowed us to really understand the resource potential of the moon. Resources not only that can be used for future spaceflight, such as those of you that want to go to Mars, but also one resource that you can bring back to Earth as an energy source, very, very clean energy source, in fusion nuclear power production, called helium-3. It's a light isotope of helium. But Neil's sample has given us a chance to understand the geological and economic potential of that energy resource. It's collected on the moon and not on the Earth, the moon, because it has no effective atmosphere, and that helium comes from the sun as part of the solar wind. Just a little bit more of history of Apollo 11. This is actually the Apollo 11 crew, Mike Collins, who flew the spacecraft around the moon, Neil Armstrong, of course, and Buzz Aldrin, and yours truly, and then Ken Mattingly here, and also, and I think we were concentrating on the Apollo 8 mission activity in this picture. It really had everybody's attention at that time. Now, the Saturn V rocket, the enabling technology for missions to the moon, and really the kind of rocket you're going to need, the capability you're going to need in order to go to Mars, back to the moon and go to Mars. It's fully fueled. It weighs 6.8 million pounds, and I'll let you do the conversion to, what is it, 2.2 divided by 2.2 or something like that for kilograms. The thrust of the 5 big engines in this first stage totaled 7.5 million pounds of thrust. Each F1 engine developed 1.5 million pounds of thrust. There are not engines like that around today. But one thing we do have today is highly reliable solid rocket boosters that are now being integrated into a new potential moon rocket called the Space Launch System. I think we'll come up with a better name for that. But it's right now the SLS, the Space Launch System. Now it gives you some perspective of the size of this. It's over 100 meters high. But here is a very large fire truck next to the Vehicle Assembly Building, the VAB, and so you get a feeling of perspective. It's often hard to really imagine. And some of you may have had a chance to visit one of the space centers where these rockets, 3 of these rockets, the ones we didn't use to go to the moon, are on display. And it's really quite a remarkable experience if you have a chance to do that. Here's our Saturn V in the launch mode just after ignition. These bright spots here are pieces of frost, of ice, sheets of ice that are coming off the rocket. Now, why are they there? Well, we actually had to stay on the launch pad about 2 hours and 40 minutes extra time. That was because of a disagreement between the the launch control computer and what actually was happening on the rocket. And the computer decided that one of the tanks had not been pressurized, and it stopped the launch at 30 seconds. We're up here in this spacecraft here, the command module, and at 30 seconds before we're supposed to launch, the computer stops the launch. That gets your attention. I think it bothered the commander of the mission more than it bothered me, because I had a great deal of confidence in what people had put together here, and that indeed we did not launch. And after about 5 minutes, it became clear that the people on the ground knew exactly what had happened. The computer had sent a signal. Remember this, those of you who use computers do what you tell them to do. It had sent a signal to pressurize the tank. The tank had not pressurized, and somebody in launch control, the responsible person, pressurized it. He just pressed a button and pressurized it. So the rocket was ready to go, but the computer didn't know it, because it was looking at the fact that that signal had not gone to pressurize the tank. And so it stopped the launch. Well, they worked around that very quickly, and in those days, you could work around it just with a wire. They just put a shunt around that part of the computer, and then most of the time was spent trying to convince NASA management that they knew what the problem was. That usually is the case. That's where you spend most of your time, is dealing with management. But that's okay. Now, what were all the components? This was the enabling technology, but it was a technology that put the command and service module on the way to the moon. We were inside this part of it during that period of time, 3 of us, and everybody who sees a command module, and you see ours at the Space Center Houston, if you go to Houston, Texas sometime, it looks very small, but remember, when you're weightless, you can use it all. The ceiling's as good as the floor. And so you really do expand your opportunities once you're weightless. And this is the Lunar Module Challenger on the lunar surface, of course, but at this time, during launch, it's tucked away in this particular part of the rocket. Just a quick picture of one of the cloud patterns over the South Atlantic that we saw in our 2 orbits. We had 2 orbits of the Earth. And I like to point out that this little band of blue here is your atmosphere. And that's, it's really a very resilient atmosphere, it turns out. It's been around for 3.5 billion years and taken care of us very well. This so-called blue marble photograph is one that I took from about 34,000 miles above the Earth. We were on our way to the moon, finally had the lunar module attached to the command and service module, and we had a moment that I could begin some meteorological observations. That I grew up with meteorology as a hobby with my father, and I had planned to actually do 3.5 days on the way to the moon, 3.5 days of observation of weather patterns. We had a unique opportunity with Apollo 17 because of where we were landing in the northern, way in the north hemisphere of the moon. We were going to view the southern hemisphere of the Earth all the way to the moon. And that's where you have much less land mass, and so these weather patterns have a much more systematic distribution than you normally would see over the northern hemisphere. And Antarctica is down here at the bottom, Mediterranean at the top. This, of course, is the continent of Africa. The intertropical convergence zone is here, and over here, just going ashore on the subcontinent of India, is a cyclone, a hurricane. And once we were on our way here, we were in a lunar referenced trajectory, and so the Earth was going to rotate every 24 hours beneath us, just like it does as if you were on the moon. And so then 24 hours later, I could see how my predictions of what these patterns were going to do were borne out. So I had a great time on the way to the moon. But this picture has become very famous. It's still, as I understand it, the most requested photograph from the NASA archives. The worst use of this picture I ever saw was in a TWA magazine many years ago, where they decided this was too empty. And so they had photoshopped Australia over into the Indian Ocean. Okay, we were headed for this point on the moon. This is the Valley of Taurus-Littrow. It's in the ring of mountains around a large impact basin, cometary or asteroid impact basin on the moon called Serenitatis. That basin's 740 kilometers in diameter. And you'll see me going back and forth now, I'll digress, between English units, metric units, and indeed nautical units. We designed our equipment, spacecraft, rockets, and everything using the English system of measure. We worked on the moon using the metric system of measure, and we flew using the nautical system of measure. And somehow we kept all of that straight, unlike one Mars mission where they got it all mixed up. Now, just for reference, Neil Armstrong landed here. About 600 kilometers difference in position. He landed on what's called a Mare surface. It's a volcanic lava surface that's been ground up. We landed in a valley, as you've already seen, with much more diverse geological features, and you'll see some more of those. The first view we had on the far side of the moon is this one, and this is not a bad representation of what you see. A slight tannish color, brownish color to the illuminated surface, certainly very black where there's no sunlight. And one thing's missing here relative to what you saw from that one picture in Earth orbit is there is no band of blue. There's no atmosphere. There's a transient atmosphere. It's called an exosphere. But it's all disappearing into space. A little bit of degassing, if you will, of the surface materials of the moon. We're learning a great deal more about that because of a spacecraft called LADEE that's been flying recently around the moon. Now, another spacecraft that's still in orbit around the moon, still very active with some very fine cameras, has been taking, is gradually developing very, very high resolutions of the entire surface of the moon. It has taken pictures of the landing sites, of the 6 landing sites, and this is ours. This is the Apollo 17 landing site, and the resolution of those cameras are illustrated by these are the tracks of the rover. And those rover wheels, only about that wide, they disturb the surface enough so you can see those tracks, but really only around the lunar module, where the surface has been winnowed, the fine particles have been winnowed, and that process lightens the surface. So when you stir up what's underneath, you start to see our tracks. This is my wandering track carrying out the experiment package that was deployed out over here. This is the ALSEP, it's called, Apollo Lunar Surface Scientific Experiment Package, and that we deployed that over here, and I was looking for a good place to put it. Now, when you're on the surface, it's hard to tell what is a good place and what isn't. You can see that I probably should have stopped right here, but I ended up over here with more craters than I would have had right there. But that's water under the bridge, or dust under the bridge, as it gets. This is the first view I had of the lunar surface outside the spacecraft. Very typical appearing surface, lots of fragments of rock, but the debris layer that's been produced by impacts, mostly, is about 9 meters deep on the average. So you have to, as a geologist, you have to learn to look through that debris layer in order to try to understand what's beneath it. This is the North Massif. It's about 1,600 meters high at the highest point. The base of this is about 5 kilometers away, or a little more than 5 kilometers. This metallic object here is one of 16 small rockets that we used. They were called attitude control rockets. Indeed, that's what they did. They didn't control your attitude, they controlled the attitude of the spacecraft and when you were in flight. they had about 50 pounds thrust. Now remember what I said about the F-1 engine, 1.5 million pounds of thrust, and there were a number of other rockets in between. So the technology of liquid fuel rockets was really advanced remarkably by Apollo. Now, 2 days later, took that roughly the same picture out the window, and you can see what we've done to your nice lunar surface. We've stirred it up. Very high bearing strength where you haven't walked, but it gets fluffed up very quickly. You can imagine damp beach sand as being that way. If you start playing volleyball on a beach sand, it's going to get fluffy. Well, that happens here. Slightly cohesive, as if it were wet. It's not, but slightly cohesive dust. The average particle size, well, let's put it this way. 50% of this material is less than 100 microns in the average diameter. So it's a lot of very fine dust has been formed. And for those of you that go to the moon before you go to Mars, you're going to have to deal with that. You're going to have to figure out a way to stabilize this surface. If you're going to have a lunar base and you're going to have traffic frequently over the same areas, you're going to stir it up like this. Now there are ways to do that. But let you think about how that would be done. Now what you need to really explore the moon for at least a short period of time is what you see here. A cabin you can live in between your excursions, a area for the equipment that you need to have on the moon, particularly the Lunar Rover, to be able to travel. We got as far as about 7 kilometers away from this base. And then, of course, another spacecraft, which is the spacesuit. And it's literally a spacecraft in which the astronaut provides mobility. But it has everything else. It has the oxygen you need to breathe. It has water-cooled underwear. That's how we stayed. I know you all have long underwear for your winters. We had long underwear, but it had little tubes sewn into it, interconnected tubes through which we circulated cold water. The water was produced, cold water was produced by sublimation of ice in the backpack. Not evaporation of water because there's no atmosphere, but you sublimate ice, you get the same effect of cooling. For the Apollo program, this was a very effective suit. It was hard to use, particularly the gloves. You wear out these forearm muscles fairly quickly and have to discipline yourself to not do that because you're going to spend 8 hours in that suit continuously. But it was good. I think for the future, for those of you that go to the moon, we're going to have to engineer a suit that's somewhat different, and particularly one that will reject dust, because you can't take these suits into your habitat in the future. Or you shouldn't, because it's the primary vector for taking that dust in. And although none of the astronauts who breathe lunar dust appear to have had a problem, we should have done a better job of monitoring that. Nevertheless, it doesn't seem that it's a problem. No, you don't want to do that. You don't want to have a long-term exposure to that dust. And there are many engineering ways in which you deal with that. I wouldn't worry about it. It's just that it's another little problem that has to be solved by our engineers. Now, I don't show you this picture to show how young I was at one time, but just to illustrate what that suit was, a little cleaner. Anything in blue is an input to the suit. Communications, water, as I said, for cooling, oxygen, anything in red is an it comes out of the suit, and the primary thing, just one major red one, is to take the oxygen and scrub the carbon dioxide out of it and then put it back into your system. The other one is for an emergency oxygen bottle. You may have noticed, we'll go back. This package up here is a high pressure oxygen bottle that would give you about 30 minutes of emergency oxygen supply if you had a hole in the suit about that big. Well, that's awfully hard to get. The suit is like armor. But anyway, we were very conservative, believe it or not, during Apollo, and so you had that oxygen bottle as well. Now, on the moon, that suit, even though on Earth it would weigh with me in it weighed about 371 pounds. On the moon, that's about 60, 62 pounds, something like that. 1/6 gravity makes everything a lot easier, believe me. And I learned in Norway, not ever having done this in New Mexico, I learned to cross-country ski. You're supposed to ski. And I found that that technique was by far the most efficient way to move across the moon, and quite fast. Because you can glide above the surface in 1/6 gravity. You don't have to slide on it, you can glide above it. And just a little bit of a toe push, and you build up your speed quite fast. In fact, I think I could have competed in the Vigelands Park 15-kilometer race very well if it was 1/6 gravity. One problem that the last 3 missions all had the problem of commanders breaking fenders off of rovers. And in our case, it was because the commander had the hammer in his, I guess in a pocket that's down here on the calf leg, and he hooked it under that fender. Well, those fenders were dust flaps. They weren't mud flaps, they were dust flaps. And so while we didn't have that fender, we were getting a forward rooster tail of dust that was, some of which was raining down on equipment, on you and everything. That's one reason our suits were so dirty, is that for a brief period of time we did not have a fender. But between the first and second excursions, EVAs, the ground came up with a fix. They looked at everything. This is one of the magnificent things about the mission control people, is that anytime there's a problem, these young men would get together, and in our case they put everything we had in the spacecraft on a table and looked at it and said, all right, how do we fix that fender? Well, what they came up with, we had some unneeded photo maps. We had, you guessed it, gray duct tape, and we just taped those maps together, clamped them onto the fender with some unneeded clamps that we had in the spacecraft that would hold lights if we needed them, and it worked very well. We had no more problem with that particular dust. And you can see here that in 1/6 gravity, these cleats would catch enough dust to throw it forward. If we'd had 1 gravity, that probably would not have happened. But now, one of the most exciting scientific sites for Apollo 17 was at a crater we named Shorty. People never knew why I named it Shorty, but it had to do with a book that was popular at the time, Trout Fishing in America. Anybody remember that? It's a Kurt Vonnegut book. Oh well. And he had a character in that book called Trout Fishing in America, Shorty. And so I just named this Shorty after that character. But that's where we found the orange soil. And you see a little bit of orange here. And that turned out to be volcanic ash. We knew that there had been volcanoes on the moon, but we had never specifically been able to sample the ash that was produced by those volcanoes. And in this case we did, and it's become a very important site because it's full of what we call volatile elements. And it completely changes our understanding of what is deep within the moon. There are still volatile materials, including water, by the way, deep within the moon, and this volcano had brought some of that to the surface. Another picture, looking back from one side of the valley across to this very high 2,100 meter South Massif, it shows you here, and you get very far away from the Lunar Rover, and you start to get very small in a very big place. It illustrates it well. And one thing also is that the Lunar Module is sitting out over here, again about 5 kilometers away. And this is the picture before the one that Kevin showed. I use it because it shows me better than his. And but his actually did show something else. It showed my footprints going down into a track behind this boulder. That boulder had rolled down the mountain about 1.5 kilometers, and it left a track in this deep dust on the side of the mountain. And so we know exactly where that boulder came from. And we also worked on another boulder nearby that came from another spot up on the mountain about 500 meters higher. And so we actually began to sample what geologists would call the strata, the stratigraphy of that mountain, just by sampling and looking at boulders at the base of the mountain. And the moon makes it very convenient a way to do geology. You don't have to climb the mountain in a limited amount of time that you have. Again, the lunar module is, you can't see it, but it's in that light-colored spot right there that you've seen before. This picture you saw, that big boulder, gives you more an idea of the scale of that boulder. They come down the mountain. It had been formed from what we called impact melt breccia. These big impacts, excuse me, keep it going, are so energetic that they actually melt the rock of the moon. And then that melted rock acts somewhat like lava for a while, and this boulder contained actually 2 examples of that kind of impact melt. Now, after the third EVA, I think it looked like I was getting a little bit tired, and I was. But this also shows how much dust. Remember that, I showed you the suit earlier. It has gotten very, very dusty, and it's still dusty. It's in the Smithsonian. My wife Teresa, who's watching back there, and I have visited you might call it the morgue in the Smithsonian, where these suits are stored in cold storage. They're actually laid out on gurneys, and you pull a gurney out with a suit that's your shape, has your name on it and everything. It's really a little bit weird. A little bit later, though, we got out of the suit, a little bit rested. Now in my underwear, apologize for that. Different underwear. This is called a constant wear garment. This is what we just wore in the spacecraft. Now, I'm often asked, what would you do if the rocket engine that was going to get you off the moon didn't light? Well, you'd worry a lot. That's for one thing. But the thing is, we had so many, we really were conservative. We have many backup and redundant ways in which we could get that engine lit. But in the final analysis, we actually have what I'm sure you call it, or something like, and we certainly call jumper cable. And that required, though, that in order to get it finally to light, that I would go out here with this set of cables, attach them to a battery back here in a battery compartment, and hopefully after I got in, the commander would put the clamps on a couple of circuit breakers, and that would immediately lock the valves open that would light that engine, and you'd be on your way. The door, of course, would still be open, but you'd be in your pressure suit, so you'd be on your way back into orbit. An actual launch here taken with a television camera on the surface shows here, not a very good picture. The commander asked me to go outside and get a really good picture, and I declined. Maybe thinking ahead subconsciously about a future political career. But everything went well. The acceleration at this point was about half a G. And that's in contrast to 4.5 Gs that we had a maximum acceleration on the Saturn V, and 7 Gs de-acceleration re-entering the Earth's atmosphere. This is what now is left, the ascent stage of the Challenger, the Lunar Module Challenger, as we rendezvoused with Ron Evans. Ron was an outstanding pilot, knew the command and service module backwards and forwards, as Kevin would, I'm sure, appreciate. Here, though, he's done a selfie. I don't know how he did this, but it's a selfie of an experiment he was running and trying to make sure the engineers who built the fuel cells that supplied the electrical power and water for our spacecraft that the engineers understood that hydrogen was leaking into the water. And that's a bubble of hydrogen that had gotten into the water, and it did always, and it didn't bother anything except, you know, when you ingest it in your food, it eventually has to come out to the discomfort of everybody in the spacecraft. But Ron was very successful in this, and this, actually, his experiment material of choice there is salmon salad. I love salmon. My wife and I eat salmon regularly, but salmon salad traveling in space didn't spoil. It just, you know, didn't taste very good. So we used it for experiments like this. So when you go into a museum and you see astronaut food, be a little bit skeptical. Remember, it's what they brought back, not necessarily what they ate. Okay, well, this was the last picture I took of the Earth. It's an Earthrise, a very nice crescent moon. Well, I think it's much better than the Apollo 8 picture, but doesn't get nearly the press. Really a remarkable view on the way home. That took another 3 days. The Earth wasn't nearly as interesting because it was dark. Remember, it was going through its phases, the opposite of the Moon. The Moon was becoming full, the Earth becoming new, and we eventually splashed down in the Pacific, not too far from the island of Samoa. And the Navy SEALs were in the water immediately from helicopters off the Ticonderoga there in the background. Put an inflation collar around the spacecraft to make sure that no rogue wave came along and sank us. And then helped us out of the spacecraft. Now remember, we've been in space for 13 days, and we actually landed in the Pacific within 1 minute of the planned return time, even though we had left 2 hours and 40 minutes late. So amazing trajectory planning by mission control. And these guys are all getting their family pictures of the astronauts coming out. There's the Tycho in the background, the helicopter that provided our trip over there. Now, if you look very carefully, this has to be Ron Evans because he was bald even then. My head was black at that time, so that has to be me, and so that leaves this Gene Cernan, and his hair is starting to get a little bit gray, which even at that time. So we're headed back over to the carrier. We changed into our flight suits, and then walked over to meet the captain of the ship. Very gingerly. Again, it's like having been on a fishing boat for a couple weeks and your balance is not nearly as good as it would have been otherwise. So it took me about 3 days to really recover my balance. Kevin probably took a lot longer. He spent a lot more time in space than I did, it's relative to the amount of time you're there, how long it takes your brain to readapt to a gravity field. Well, there's the enabling technology again. Just wanted to make the point that we're going to have that kind of capability if we're going to go on back to the moon and then to Mars, which is probably the best path to take. So if there are any questions, I'd be happy to take them. Newest sports ball. Questions? Any questions? Yeah.
Why did you become to be an astronaut? Why did you choose to be an astronaut?
Why did I choose to be an astronaut? I was working with the United States Geological Survey, had begun to be interested in space because when I was in Norway in 1957 and 58 as a Fulbright student, that was when Sputnik was launched, and that got my attention like it got the attention of almost everybody in the world. That was the first artificial satellite of the Earth, and so I started to pay some attention to what was going on in space. And when NASA asked for volunteers, NASA and the National Academy of Sciences asked for volunteers from the scientific community in 1964, November as I recall, I thought about 10 seconds and raised my hand. I ought to do that. And if somebody goes to the moon and I had a chance to volunteer, I felt, well, I would probably regret it the rest of my life. And so that's when I volunteered and was ended up being selected. There were 1,400 volunteers, and out of that 6 were selected. So I felt very fortunate. But I was in the right place at the right time and prepared. That's what you have to remember, you know, is always be prepared for the opportunities that you never thought were coming.
You were the first scientist on the moon, actually the first scientist astronaut at all. Did that put an extra pressure on you to perform, and how were you viewed by the jet fighter pilot astronauts, so to speak?
That's a great question. I always feel pressure to perform, and I don't think that that changed much. It was an opportunity to not only participate in a great human endeavor and an important geopolitical endeavor, but it did give me a chance to practice my profession in a very unique way. And so I felt like I was more than ready. I had had the opportunity, delightful opportunity, to become a jet pilot, flew T-38s while I was with NASA, and helicopters. We were talking about that this morning. And so it was a great honor and privilege for me, and a great opportunity to learn a whole bunch of new things. Initially, there was a reluctance on the part of what we call as the astronaut office, and particularly Deke Slayton, who is our boss, to have scientists and engineers who were not professional pilots in the program. And if you ever read Slayton's book called Deke, it's an excellent book, and it reads just like Deke talks, and he's very frank about it. He thought his pilots could do whatever they were asked to do. But on the other hand, the reason the pilots were there is because they were experienced, they were professionals in their field. And so if you want to do exploration, you want professionals who are experienced in exploration. So the logic the National Academy used to persuade NASA to have scientists in the program, I think, was excellent. I also think the logic that Slayton, well, it may not have been his logic, but it was very important that we become jet pilots at the same time. And that helped, I think, to bridge the gap with the pilot community. And also helped me because once Neil had landed on the moon, the pilots were looking for other things that they could do that were different than just landing on the moon. And I was able to provide the training to the pilots. I put together their training program, and Al Shepard, who was my boss, immediate boss at the time, agreed that if Jim Lovell and the Apollo 13 crew wanted to go shoot that program, well, then have at it. And that began a very, very extensive, about a week, a month training for the crews that ultimately went to the moon in field geology, which is my profession. And I think it added immensely to the scientific return of these missions, and gave the pilots something to concentrate on that would be very, very different than their normal expectations for just going to the moon and coming back.
Okay. Mm-hmm. Thank you.
Back there? You want? Okay. I'll let you.
When you were in the spacecraft, did you feel any kind of fear or anxiety of like anything that could happen?
That's also an excellent question, because as you know, Apollo 13 did have something happen that really did challenge the national system. But after 15 months of training for a mission, and particularly after becoming a jet pilot and helicopter pilot, you know, you take those kind of things as part of what you volunteer to do, and they don't weigh on your mind. They really don't. You think you're prepared, and I think you are prepared to deal with any emergency that comes up. And so once you're convinced of that, then you don't worry about it. And you also know that in the case of these space flights, that there are thousands of people who are going to help you if you have a problem. And I may have developed more confidence in mission control because I spent a lot of time with the flight controllers. They're good friends. I go down with them they celebrate the Apollo 11 landing every year, and I spend time with them. And I think when you know the people who are going to watch out for you, it's very, very important that, and tends to get those kinds of ideas of fear or anything. Now, excitement, yes, great deal of excitement. It's always interesting and exciting. There's something new happening all the time. Kevin, you're going to have to control the time. I'm fine.
Well,
I'm fine. We can do
I was going to try to get you out of here by 10:15 if we can.
whatever. Yeah.
We have one question here.
Oh, yeah. Back.
What's the biggest problem for being an astronaut?
What's the biggest problem of being an astronaut? The biggest problem probably comes after the flight, because all of a sudden people are asking you questions, and you have to be prepared to answer them. and this is a minor point, but for 6 months after the Apollo 17 flight, the crew toured the United States and many countries in the world. And my challenge during that time was presented by the commander taking what I said. I always spoke third on the program. And I would, whatever I came up with to say that in a particular event, and we were doing 6 and 8 events a day. And I would say, well, the next day, the commander would start to use what I had said in his talk. So I had to come up with something new 6 or 8 times a day. And that was a challenge. But I think more seriously, probably the biggest challenge that I had at the age of 30 was actually learning to fly jet aircraft. When Kevin probably learned at the age of 18 or 20, right?
Yeah.
Yeah?
That's true.
10 years makes a big difference. And particularly when you had a profession that requires that you concentrate on things in order to understand them. Well, you can't do that when you're flying a high-performance aircraft. You've got to have what they call a scan. And you got to take pieces of information and keep taking those pieces of information and always integrate them into the total situation. That's very different than being a scientist, believe me. And at the age of 30, I had to learn how to do that. And that was a challenge for me. But eventually, I think I conquered that challenge, became a pretty good pilot.
Maybe like 2 more, and then we'll try to
Okay.
get one to his next event. So,
could you describe the sounds that you heard inside the spacesuit on the moon from your PLSS or when you were hammering the rocks? Did you have any ambient sound at all?
Oh, another excellent question. Most of the sound in the suit were fan sounds that were circulating the oxygen and the water. And the vibration of those you feel and hear in the suit because there's atmosphere in the suit. And that's something you always want to hear. I know when we had our rest periods in the lunar module, I would always be on watch. I would wear the communication hat. And I'd wake up about every 2 hours and just listen. Because you want the sounds to be very familiar. And then I go back to sleep. I didn't have much problem sleeping on the moon. Now, with respect to other sounds, I could feel through my boots the hammering on. If my partner was hammering on a rock, I would feel that because that debris layer has what scientists would call a very high Q, and it transmits sound very efficiently, seismic sound, vibration. And so I could feel that through my boots. So that was the only other kind of sound that you heard. But it all had to do with those two things. One, the suit was an enclosed atmosphere, and you could get vibrations through the atmosphere and the suit itself. And then the fact that the soil was very efficient in transmitting sound. In fact, when a meteor hits the moon, it rings, and the sound goes around the moon and around the moon. It lasts. From our seismic, we had seismographs on the moon, and sometimes those impacts would ring for an hour. You continue to get that sound coming through the moon.
Before we do the last question, because I want his voice to be the last one you hear today, but before we do that, I did want to just say just a couple quick thank yous. And the first one is, I didn't say it beforehand, but he's here for Starmus, which I know you're all aware is happening this week. It's a very big event in Trondheim. But he called and he said, you know, Starmus isn't really accessible to everybody, and I really want to speak to the people of Trondheim and to the people of NTNU if we can, and can you set up a public event for us? So he got in, his travel to get to Norway, I think, was longer than his travel to the moon because he had flight cancellations and so forth. He really got in late last night, and he's doing this event just because he wanted to do an extra event to come out and be with the people of Norway. So when he's done, make sure you give him a big round of applause for that, and that is very, very much appreciated.
Well, let me return that, Kevin, because, and really, I guess the person that deserves the credit is Drew Fuchsel.
Drew Fuchsel set us up.
Because he's a mutual astronaut colleague of ours, and he said, well, Kevin's over in Norway. And I said, really? What in the world is he doing there? And I found that out, and so I got in touch with him, and Kevin put it together. And again, the Starmus people brought me here, and they deserve an awful lot of credit for making this possible.
So Starmus brought them, and NTNU sponsored it, and thank you to Litteraturhuset and the Bibliotek for hosting the event. But I wanted to make sure that I said thank you for doing the extra work, because there are a lot of people here who aren't doing it, going out and doing the extra work. It takes special motivation to do that, and energy. So thanks for doing that. And we will take one more question, and then I'm going to try to sneak him out of the driveway by 10:15 and move on to the next thing. So you got one more. Yep.
Hi, so thank you very much for a very interesting lecture. I just wanted your take on the future. As you've talked about Mars, SLS, how do you look upon NASA's plans with the Moon as a gateway compared to SpaceX and the ITS? And what are the biggest challenges for our future and going to Mars and that part of the plans?
Oh, okay. Well, I won't take the rest of the day. But my feeling is that just from a managerial point of view and a technical point of view, the fastest way to get us to Mars is by way of the moon. We need to relearn again, and by we, I mean, that's a very expansive we. Everyone who's going to be involved, whatever countries are involved, we need to learn how to work in deep space again. It's a high-risk environment. Nearer space now is reasonably accessible. And it's still risky, believe me, but deep space is very special. And we need another generation or two of young people who learn how to deal with those risks and the challenges of deep space. And I think the best way to do that is to do it 3 days away rather than 9 months away. And so that's one of the major reasons, operational reasons, why I think the moon is very important in a Mars program. This is not news to anyone that's followed what I've recommended. But there are also, though, the resources of the moon can be very important to spacecraft and human beings going to Mars. And the nice thing is that as you're working on the moon and preparing for Mars, you learn a lot of new science as well. It's not just standing in place. And that of course, excites me as well. There are going to be some challenges. We don't know how to land on Mars, for example. We need to work those things out, both in high Earth orbit and on the moon. Mars has just enough atmosphere to make it difficult to land and not enough to help as the Earth's atmosphere helps us to come back. And getting to Mars, say 9 months plus or minus a month, it exposes you to the radiation of space. We need to deal with that. I think there are many shielding ideas that come, but one of the best is having a water shield around your spacecraft. The moon's a source of water. You can make water anywhere on the moon, and at the same time you may be producing some other resources that will be important: oxygen, hydrogen, and this energy resource that I mentioned earlier. That energy resource is not only can be important here on Earth as a very clean fusion fuel, highly efficient, but also enables private sector and government cooperation, because that production of that energy resource could be most efficiently done through a partnership, I think, with the private sector and government. Now, is NASA thinking that way? Probably not at this point. And they have not yet been directed, as far as I know, how to think by the administration. It really is for the United States to be involved in deep space. It's going to take a presidential decision. You need that kind of leadership in order to make these kind of things happen. We've seen that many, many different times throughout the history of the United States, and so we're just sort of waiting to see how that develops. And hope some of us are trying to influence that decision, but who knows how those decisions finally are made. I haven't been in that particular building. So yes, I do think that Mars is a legitimate next major objective, but I think we have to be very smart about how we do it, because it's not going to be easy and it's going to risk. Now, I also would say that, and Kevin may have an opinion on it, that if you do put together a Mars mission and you're there, and you start to have, and you're in your landing sequence, which is very fast. It doesn't take very long to get out of orbit and onto the surface of Mars. And you start to have a problem that you will abort to the surface. You won't spend all that money and effort and come home. You'll abort to the surface and figure out how to fix the problem. That's a new psychological thing we have to think about. And it will affect the engineering of how you do it, but I think it's very, very important that we don't think in terms as we did in Apollo, that if you have a problem during landing, you abort and come home. We would have done that in Apollo, but I don't think you want to do that for Mars. And so there's some very interesting philosophical, psychological issues that are going to have to be addressed. Ladies and gentlemen, thank you so much for your attention.